morning. Welcome. So yesterday we looked at first at the linear advection equation, shortly also already at the wave equation, and then we focused on the numerical discretization of the linear advection equation. We saw that the forward time-centered space scheme doesn't work, it's simply unstable, but that the explicit Upwind method works. So first we want to have a little recap on that. So there we argued, instead of taking the difference approximation in space central, as we did with success for the diffusion equation, heat equation, here we have a different thing. Here we have a propagation problem, and the information is coming along the characteristics. So, and in our case, an unknown initial condition, and the initial condition of an unknown is simply transported. It is not changed. So therefore it makes sense to take the difference approximation, and that means the slope of the solution, from upstream, from where the information is coming. So that gave us then the idea then to do the discretization in the following way. We take the time discretization with the explicit Euler method, and the space discretization we take then Upwind. And that is the case for C greater than 0. Because then information is flowing from the left to the right, and upstream is then to the left. And then we do that. And the stencil that we get from that is, and we have our point J, and we have the J minus 1, and we have the value to determine. It is the stencil like that. So that is J minus 1, that's time level n, and n plus 1. So that would be our difference stencil that we have for this method. So what if C is smaller than 0? We have not seen that yet, but that will be your task for exercise 6. So then we put our finger in the air, and then we recognize flow is coming from the left. Okay. So then we have to take the difference approximation, to the right. So we then have to take it from the right. So we have then to take J plus 1 and J to take the slope. So then I call that 17 star. That is then we do the same approximation in time with the explicit Euler method. But for the space discretization, if C is negative, we do it now by taking uj plus 1 n minus ujn divided by delta x is equal to 0. And that is for C smaller than 0. So the difference stencil for that then looks, we have the j here, and then we have here the j plus 1. Here is our unknown, and then it looks like that. So this is time level n, this is time level n plus 1. So that is then our difference stencil. And if we think of the characteristics, then the characteristics will go hopefully like something like that. So that would be the characteristic, say dx of t dt equal to c, and that is then smaller than 0. And we argued yesterday for the stability condition, we should have this point where the characteristic is coming from at the old time level through the point that we want to determine. We should have this point within the interval where we determine the numerical solution. In that case, this point should be then between xj and xj plus 1. So you can think yourself what that gives them in regarding the stability condition. So then we have that, and now we want to continue with the analysis of this method here. first we can have a look at an example, and that is now for this case here, for when c is greater than 0. Then we have the Upwind method, and we want to see here what is happening. First I explain you the initial condition here. So we have x in this direction, and we have the unknown u in this direction. This is an example, for example, that we could have in heat transfer. In this example, a heat discontinuity in temperature is entering at time level t equals 0. So you see here, if we say this is temperature, then we have 1000 Kelvin or Celsius. So you have 0 degrees Celsius, and here we have 1000. And then this discontinuity enters and will be just propagating. This is now first calculated with a current number of 0.25. So then we can see what is happening. The red line is the exact solution, and the dots are the numerical solution. So you see what we get is a smearing. That is something that is typical for diffusion, which we don't have here. So we have here a combination of advection and diffusion, and we shall understand in a minute why. But this is a numerical error, because we should have something that is approximating this discontinuity, but we have something that is smeared, and we can investigate how this depends on the current number. So just to remind you also on the current number, which we are varying here, that is, we call it capital C, and that is our advection velocity c times the time step divided by the grid spacing. So, and we had derived the stability condition in this case that it should be between 0 and 1. And here you think yourself. So now we can vary the current number here to see whether we can get something, can understand the dependence on this. So we change it to 0.5, and we run it again. So now it goes a little faster, but we still have the problem. We still have the smearing. So here we have it now to 0.5. It might have gotten a little bit better, but not really that much. So, but if we do now dramatic, well, first we try to get close to the stability limit. First we tried 0.9. So then, because 1 is the limit here. And then we see what is happening. So now it gets the diffusion that we see here, where the discontinuity is smeared, gets smaller. So we are then on the right track. And if we choose it simply at the stability limit, and we shall understand in a minute also why, then we shall see that this is a good choice. So now, no diffusion at all. We capture the discontinuity exactly. So that is that's the right way to do it. We'll see that why in a minute. And you shall also think about that when we have this situation here. Here we have a propagation from left to right, but you then think about it and then a propagation from right to left. Before we continue, we want to look at another problem here, and that is when here we have a discontinuity, which is interesting in itself, but now I want to look at a sine wave propagated, and here we will have periodic boundary conditions, so that when the sine wave is leaving to the right, the value there is entering from the left. The values at the boundaries are the same. What we talked yesterday about periodic boundary conditions,
let's see what we shall see what the this is a very coarse grid to see the effect. So I have only 11 points to represent the sine, so that's the initial condition. And we start from not from 0, because we know, because of periodicity, the value that we have at 0, which is our point x0, is the same as we have at x equal 1. So then here the sine is 0 there. So we have here a very coarse grid. So here is x and here is u. That is the initial condition. And then we let it go. It goes very quickly. And what we see here after, let's see, we can check it the time. It was 1 or 2, I don't remember. We can check that in a minute. The exact solution in that case should have just reproduced the sine. Should just be at the same location again, because when it's leaving here, it's entering on the other side. So we just let it propagate. But what we get here is a complete diffusion. So the wave amplitude has gone down from 1 to a little bit, well, it's 0.05 or something. So a very large diffusion. We call that dissipation error. So the amplitude is simply vanishing. That is, it's lost. And so that is an error that we have here. We can improve on that error if we refine the grid. So let's see, look at this function. And we can also see what is the t end. Yeah, it was 2. So it was 2 periods propagating. That was a CFL number of 0.5. So we can do the same thing here. We can also vary the CFL number. Let's do that first, then we have this. We do that first before refining the grid. And then we can see what is happening. So everything is happening very quickly here. Now the amplitude has become a little bit higher. So also here, it seems that for larger CFL numbers, for larger current numbers, we get better accuracy. And we can also try here our favorite choice, 1, and see what that results in. So then we let it go, and it perfectly reproduces the result. So also here it is exact. And as promised, I also want to show a variation of, so we change the current number again to have it, so you can take it back to 0.5. And now we refine the grid. So we see we had only 10 points. Now we take the double. So we have now the current number 0.5, and we have doubled the number of grid points. So now we see a little better representation of the sine. Okay, so now we have still a problem, but before the amplitude was damped around 0.1 or some in this region somewhere. Now it is at least getting better. So by doing grid refinement, we can improve on the results. But still we have a problem. We have here, we see very clearly the error, and the error is a dissipation error. So the amplitudes get damped. They should stay unchanged, just the propagation of the profile, but what we see is a damping. That is a dissipation error. Another error that we cannot see in this example very well is that the propagation velocity is not completely correct. So the waves are not propagating in the correct velocity. It's small, therefore it's hard to see it, but if we would look at this point here in detail, not for 0.5, that is a special case, but for 0.25 or larger, for smaller than 0.5 and larger. 1 is again exact. We will see that the propagation velocity is not completely correct. And that is called dispersion error. We'll discuss now these errors by analyzing the method in more detail. And we shall do that for the case when c is larger than 0. So we shall focus on this case here that we
also discussed yesterday. So it will be this case here. So to do that, we shall look at a technique that is useful for this analysis, but this will not be part of the pensum, but we do it here to do so that you can understand it. So you should be able to interpret it, but it's a little bit technical, so therefore it is not part of the pensum. And what we want to do is, we want to find the equation that we are really solving when we are using this method. So to find the equation which in fact is solved by the first order explicit Upwind method. We use here a technique called modified equation approach. So we can apply that to any difference method. We apply it now to this difference approximation, to the explicit Upwind method. So what we do here, we insert a smooth function in here to see what equation we are really solving. So we have A. That's what we're going to do for exercise 6. So for the modified equation approach, we insert a smooth. Now it is a solution u of xt, not of the PDE, but of the finite difference method that we want to solve. In that case, it is then our explicit Upwind method. So we want to stress that it is not exact solution of PDE in that case. What we do for the truncation error. Truncation error, that is not 0, but we get some order delta t and delta x. We insert then that into equation 17. And we do the usual assumptions that we assume that x is xj, that t is tn, so that we don't need to write that much in the end. We can skip the indices. And then we have the following, 22. So now we insert then the exact solution of the PDE, of the finite difference method, not of the PDE. So that will be u of x, and that will be tn plus 1, that is t plus delta t. So that we are using here. This is then minus u of xt divided by delta t plus c. Here we do it similarly. We have u of xt minus u of xj minus 1, that is at x minus delta x, t divided by delta x. And now, since we are now taking the exact solution to the finite difference method, this is 0. That is the difference from the modified equation approach and the truncation error analysis. In the truncation error, we insert the exact solution, and then we find out by Taylor expansion what we get. But here, we assume that we have a solution of the finite difference method. So therefore, we have a 0 here. And now we do the usual Taylor expansions to see what equation we are actually solving when we use the explicit Upwind method. So that is the Taylor expansions. We do it around the point xt, which we skip when we write it. And Radar told me that you have this actually in Maple. You have the function Taylor, where you could do these Taylor expansions, say, have help from mathematical simulation tool. And I'm sure you'll also have that in Mathematica. So what we have is u of xt plus delta t. That is the usual Taylor expansion. It's the same as we did before for the exact solution. Now this is a smooth function, we assume that. So we can do the same Taylor expansion. So it's u of xt, which we skip, delta t times the first time derivative, at xt plus the delta t squared half u t, and we take also the third order term, that is delta t to the power 3 divided by 6, and the third time derivative. And that is then remaining order is then delta t to the power 4. We also need u of x minus delta xt over there in 22. So Taylor expansion around xt now is u minus delta x ux plus delta x squared half u xx minus delta x to the power 3 divided by 6, third space derivative plus order delta x to the power 4. So now you insert that into the finite difference method we have here to see what we get. So these Taylor expansions are inserted. Taylor expansions around that, they are inserted into 22. And then we get following. So we have the u plus delta t ut plus delta t squared half ut plus delta t to the power 3 divided by 6, third time derivative over delta t to the power 4. That is our u of x t plus delta t. Then we have minus u divided by delta t. Let's take that away here. Now we have this term here, plus c times, first is just u minus, now we insert what we have for u of x minus delta x. So u minus delta x, ux plus delta x squared half ux minus delta x to the power 3 divided by 6. Third space derivative plus order delta x to the power 4. So that is divided by delta x, and this is equal to 0. So now we have that. Now we can simplify things and see what we really get in the end. U cancelled, we can factorize delta t. And here u also cancels. We can factorize delta x, and then we get the following. That is then the equation that we are in fact solving. So we get ut from here, and from here we get c minus minus plus cux. Now we write the rest on the right hand side to see that we are not solving this linear advection equation, but we are solving another equation. So we move this term here now to the right, therefore minus delta t half utt, and if we just collect the other time derivative terms, we get here minus delta t squared divided by 6 third time derivative, and then we have here order delta t to the power 3. So that is coming from the time derivative. Now from the space derivative, this way, don't need that any longer. And from there we get here delta x half uxx. And that is here with a minus sign, so it gets with a plus sign on the right hand side. It has c in front. C delta x half uxx. That was this term. Now this term has a minus minus, so it has plus. It gets with a minus on the right hand side. That's c in front, delta x to the power 2 divided by 6, third space derivative, plus order delta x to the power 3. So it's this equation that we are in fact solving. It's not the one that we want to solve. The one that we want to solve is ut plus cux equals 0. So we are solving a much more complicated equation. And now to see even more, we try to eliminate the time derivatives to replace them by the corresponding space derivatives. Because then we have, say, our PD on the left, and the right hand side we see then the dependence on space rather than time. And that makes it easier to interpret the equation. So that is now a technical thing. I write it. We eliminate the higher time derivatives that are those on the right hand side, especially this one here, if we want to go further, also this one here. In 23, we do that by repeated application of this equation, a repeated application of 23. For example, this term minus delta t half utt. To eliminate that, we take the following. So that is eliminated by taking delta t half times the first time derivative of this equation 23. Why that? Because then we get here the second time derivative. And we have it with a plus sign, then let's see. Then we can well, if we have this with a plus sign, then if we would write it, we have it here on the left hand side. If we would want to have it on the right hand side, let's see. So we take that, we get the second time derivative, And if we, let's see, if we, well, we could, if we have it on the left hand side, then it, let's see, if we have it on the left hand side, so this, and if we add it to that, we would like to have it then as a positive, right? So if we have it as a positive, then we will have that here, as we'll then have here the, we can do it, we have then the delta t half, the utt, and that we can then express, and it will be then the minus c uxt. So we'll get another time derivative of this, which we then have also to eliminate. But this term here, then we can replace that, we can replace then this one here by what we get here. So that is the idea. So then we can eliminate this term, and also the other time derivatives we can then eliminate this way. So the trick is that we replace then time derivatives here essentially by the space derivatives. And we can also take higher time derivatives, then we get also larger other further derivatives of that, but we can replace one after the other. So, and that is a little technical, and yes?
23. Hvilken ligning er det egentlig?
Oh, sorry, that I have written the wrong number. Thank you. So this is 23. I was giving the same wrong number. Thank you. That is important. So it is this equation here. Because that is the equation that we are actually solving. So then with this trick, by replacing time derivatives by space derivatives, using this equation, higher order derivatives of t as well, then we can get rid of these terms here, and you can find that in the book in table 4.1. That is in Thatcher, Henderson, Tannehill. That is the 213 edition, which is on page 107. And this, for the second edition, is Taylor, Anderson, Fletcher, 1997. There it is on page 105. So there then you see also the way they do it. You make a table, and then you try to identify the terms that you want to eliminate, and then you do the corresponding operations. So the result of this, and that is a little tedious, it's one page. Let's see, I can show it to you. So that is from the second edition, this one here. It's hard to see. Let's see, first we have to see it. So here it is. So I have to make it a little bit bigger. So this is our equation 23, corresponding to that. They put here the time derivatives here with the plus sign on the left hand side, and
here as also still on the left hand side. And then we do this multiplication here of the equation for 10, it's our equation 23. And then we get here the minus delta t half times the utt. So that is then coming from here. And then we get in addition then this mixed term minus c delta t half uxt, that is this term. And then we get also higher time derivatives from this. If we have the utt on the left hand side, we multiply by delta t half, we get then this term here comes from there, and so on. So and then we can do this, and we can then also eliminate this term that has appeared here by doing a multiplication of c half c delta t half ddx of the equation. So then we get here t dx. So then we can eliminate that and so on. So it's a little tedious, but it's possible then to eliminate all the higher time derivatives from by applying the equation several times. And the result is the following. That is applied several times. Then we get the following. Let's see. So, this process of elimination of higher order time derivatives leads then to the modified equation. In our case, that is of the first order Upwind method, and we get the following. That is 24 ut plus cux, that is the equation that we want to solve. But what we get when we do this process, let's see, that also in here. That's too much. Well, it's hard to see, but in the end, we sum up all these terms in the table, and what we get then as the first term on the right hand side is our advection velocity c times the grid spacing delta x divided by 2 times 1 minus the current number. So this is the little c is the advection velocity, the capital C is the current number. It is multiplied by uxx. And then we get a term again with the advection velocity c, delta x squared divided by 6, 1 minus c. Then we have here 1 minus 2c. These are the current number again, times the third time derivative. And we get, so that is how far it is done here. We could go on, but that is not so interesting. These two terms tell us already quite a lot. And the error terms will be of order delta x squared, x to the power 2, delta x squared delta t, delta x delta t squared, and delta t to the power 3. So this is the equation then, at least with the leading error terms of first and second order in delta x that we are in fact solving when we solve the linear advection equation by the explicit Upwind method.
And what does this tell us? It tells us that we do not solve the equation that we want to solve. We solve a much more complicated equation. This equation contains something on the right-hand side that has the same form as a viscous term. If you think this would be, say, the incompressible Navier-Stokes equations, then we would have derivative of the velocity, we would have convection term, a little bit more complicated than that. But this would be then the viscosity. So therefore we call this here the numerical viscosity, this term here. And that is responsible for the diffusion, that the amplitude goes down, that the discontinuity gets smeared. That is responsible, this term. That is then a numerical diffusion that we are introducing here by this numerical viscosity. And we have here another term. I call this coefficient here, I call it A3. Of course, if we would write that as coefficients from that would be A2, numerical viscosity would go on, then we would see we have coefficients here with higher order space derivatives. And this term is responsible that we do not get the propagation velocity right. This is called dispersion error. So let us first note this, what I just said. So the nu, that is the advection velocity times delta x half times 1 minus the Coulomb number is the numerical viscosity of the numerical method. And the term that this is then governing, that is the numerical viscosity nu num times the second space derivative of our unknown. That term is responsible for the dissipation error. And the dissipation error, that was the error when we had a solution. Say we had x and we had u, and in our example it is something is propagating, so we should have something like that, but what we get is something that is damped. So this error here, that is, so this is exact, and this here is the numerical, and that is then the dissipation error that we see. So that is the error that makes the amplitude decrease. So we lose the amplitude simply because of the dissipation error. The term that we have here, the A3, is not known the name. That is the term, in this form, the A3, the third derivative, that is responsible for what is called the dispersion error. And the dispersion error, that means that the velocity of the wave is propagating not correctly. So that we can see the following way. So if we have the same problem as over there, so we have x and we have u, and then we say we should have something should be like that. That should be the, say, that would be the exact solution. But what we observe numerically is something in the ideal case, not with the method that we are discussing here. That would be something where we simply lag behind. So this would be, say, numerical It would not be with our method because that would be too dissipative. But this error here, so that is the dispersion error. So this error here, that we call dispersion error. It is, in that case, numerical solution is propagating too slowly. So that is then this error here, so that we are then, it's all shifted by this distance, that is the error in the propagation velocity times the time that has gone. That gives us then the wrong location. It is like you want to compute sound, and then you want to know when it is arriving. And with a numerical method, it would either arrive too late in this case, or you could also have the option that it is arriving too early. So then that's not good either. So it is these terms that we can identify as responsible for these different errors. Dissipation error, error in the amplitude, that is decreased simply by numerical dissipation. The dispersion error, which is then leading to the wrong propagation velocity. Okay, so then there is another thing that we can also note from here. We can look at that also after the break, but I already say it now. And that is when you go back to the modified equation of the explicit Upwind method. We see here a particular case, and that is the case when the current number is 1. Then this error term will be gone, this error term will be gone. If we would continue, we would get rid of all error terms. And that is something that is very special. We saw that in the examples. For c equal 1, if we have a positive propagation velocity, the explicit Upwind method is exact. Let us look at that after the break, which we take for only 10 minutes, so that we can finish 5 to 10. Okay.